Hello, my name is Alan Loy, and today I'll be discussing my capstone research project. Now, just to give a brief overview of what I'll be discussing, first I'll discuss the rationale for my project. Then I'll state the two main goals of the study and a list of criteria that I used to develop the software tool that came from this project. Then I'll discuss the methods that I used to make this software tool, and lastly, I'll conclude by sharing the results and the major findings from this study. Now, adenosine triphosphate, or better known as ATP, plays pivotal roles in cellular metabolism as the fundamental unit of molecular energy, and in cellular communication as a bound ligand. However, ATP plays other important roles, such as in cellular signaling, and to identify these other roles, it is crucial to analyze the binding of ATP by a protein, which should be modeled as clearly and as accurately as possible. However, existing methods of evaluating this quality, called the regional structural quality, have used arbitrary units of measurement, making them very unreliable. And although a software tool called PDB-EDA was developed to establish a more universal unit of measurement, it itself was limited in that it could only analyze small spherical regions around small atom ligands. Now, in this study, the data used came from the Worldwide Protein Data Bank, or the PDB for short, and which manages the access to data for all known proteins and other kinds of biomacromolecules. In this study, there were 4 statistics that were retrieved for PDB entries containing an ATP ligand component. And these 4 statistics were used in the previous iteration of PDB-EDA to evaluate the regional structural quality. And so the first statistic was the electron density resolution, which refers to the level of structural precision within an electron density map. And more specifically, it measures the minimum length of an atom that can be observed with its accompanying electron density. And it's measured in angstroms. So for instance, in the maps on the left, you can see the top map is the good example with a very low resolution, which would mean that you can see more detail within that model. But the map on the bottom, you can't really see as many of those purple meshes, which indicate the electron density. And as such, it has a very low regional structural quality. The next metric that was used was the atom occupancy, which is found for every single atom, and it refers to the proportion of all possible crystal conformations in which that atom is found at the exact same spot. So for instance, an occupancy of 0.5 for an atom would mean that that atom is found in the same spot in 50% of those conformations, which means that in the other 50%, it can be found in varying locations, which would make it very difficult to predict the modeling and thus make it a very low regional structural quality. And you can see this in the maps on the left, where the map on the top is again the good example, and the map on the bottom shows faded images of atoms showing that that's also where they could be, and thus indicating a very low occupancy. And so for this study, actually, there is just one occupancy recorded for every single residue, which is another name for an ATP ligand, since there were usually many different atoms within the residue. So there's just one occupancy, the minimum atom occupancy recorded for every single residue. The next metric that was used was the distance between symmetric atoms. Symmetric atoms are identical atoms found in neighboring crystal unit voxels, which is another name for the unit of a 3D map. And the reason why they were used is that the closer together these identical atoms are, since they have the same electron densities, that could increase the amount of steric hindrance within that entire region, and thus causing the atoms to shift around and thus reduce the overall quality of that model. And so just to illustrate this, on the map on the bottom, you can see those atoms that are colored the same, that have the same colors, are located very close together, indicating that there is probably a lot of steric hindrance within that region, and thus very low regional structural quality. And just like with the atom occupancy, since there were usually many different atoms within every residue, there was just one distance recorded, and that was the minimum distance. Now, lastly, the fourth metric was the significant regional discrepancy, and this refers to the deviation between the calculated and the observed positions of electrons. And this was actually found to have the greatest effect on the regional structural quality in the previous iteration of PDB-EDA. And so, as you can see, to illustrate this, the map on the bottom and the left, you can see that those faded images are also showing the electrons around them, and you can see how they're kind of not in where they're predicted to be. And so this indicates a very low regional structural quality. And actually for this study, there was both the observed and the expected discrepancies that were calculated to see how accurate existing methods were for predicting the regional structural quality. So now, this brings me to the two main goals of my project. The first one being to expand PDB-EDA to analyze not just small spherical regions around small atom ligands, but also more complex regions around more complex ligands. And in this study, ATP was used as the test ligand, but the goal of PDB-EDA is to make it customizable to analyze other kinds of complex ligands. The second goal was to evaluate the other three statistics, namely the resolution, occupancy, and the symmetry, to see whether they still were accurate indicators of the regional structural quality, because they were found to be so in the previous study. But now in this study, we wanted to see whether they were still accurate indicators for a different kind of region, a different kind of ligand altogether. And so before I went on to write the programs to expand PDB-EDA, I first made up some criteria for these new programs. The first thing is that this package should be able to retrieve the three standard statistics and the regional discrepancy. It should be written in Python 3, since the previous iteration was written in Python 3. It should be able to very efficiently process data sets of virtually any size. And it should be very portable in that it should only require an MS-DOS or a Linux command line to run. And lastly, since some PDB entries they don't have the data needed for retrieving the statistics, if the program does run into those entries, it should just indicate that to the user through some sort of error messaging, and then just move on to the next entry, ignoring that failed entry so that that failed entry doesn't interfere with the overall calculations. And so now, with this list of criteria in mind, I went on to write 4 files that expanded PDB-EDA that accomplished these 4 tasks. So the first 2 files were fetch PDB and fetch CCP4, which, as their name suggests, they retrieve the PDB and the CCP4 data. Now, the difference between these two types of data is that PDB refers to the structural characteristics of the entry, and the CCP4 data refers to the electron density map data, more specifically the FO minus FC data that would then give me information about the deviation between the observed and the calculated positions of the electrons, which I then used to find the fourth statistic, the regional discrepancy. The third file that I wrote was called main, and as its name suggests, it did the main task of retrieving all of these statistics. So for the first 2 statistics, the resolution and the atom occupancy, they were actually very easily retrieved because they were already located in the PDB data. So all I had to do was just to call the resolution and the occupancy, and then from there I could get the data that I needed. The symmetry was derived from each entry's own unique remark symmetry record. And then from there, I could get a list of symmetric atoms that I then used to find the minimum distance between symmetric atoms. And so now for the regional discrepancy. As I mentioned previously, I found the expected and the observed regional discrepancies. So I'll start with how I found the expected. First, I got a list of all the voxel discrepancies within the entire PDB entry. Then I found a significant density cutoff that was based off of 3 standard deviations away from the average discrepancy for the entire PDB entry. Then I found the absolute value of all of the individual voxel discrepancies, since some of them could be positive or negative. And then I compared them each to the significant discrepancy to then find a filtered list of significant discrepancies. And then from there, I then added them all up to get a sum. And then with that sum, I divided it by the number of voxels within the entire PDB entry to get the average absolute voxel discrepancy. And then with this average value, I multiplied it by the number of voxels within the region, which is defined by a 3.5 angstrom radius around the ATP residue. And then from there, I got the significant expected regional discrepancy, which is what I wanted. Now for the observed discrepancy, there were similar steps taken. But for the first step, I got a list of voxel discrepancies, but this time not for the entire PDB entry, but just for that particular region. Then I found the significant density cutoff and using a similar process to how I found the cutoff for the expected discrepancy. And then I compared each voxel discrepancy to this cutoff to find the significant voxel discrepancies. And then from there, I sorted them into positive and negative discrepancies, just in case a researcher needed to differentiate between these 2 types of discrepancies. And then I found the absolute value of all of these discrepancies, added them all up to get the observed regional discrepancy. And lastly, the fourth file that I wrote created a spreadsheet of all 5 of these statistics for every residue for every PDB entry. And so in the end, when I ran this program, it took around 2.5 hours for 871 residues, which were corresponding to 600 PDB entries, since there could be multiple residues within every PDB entry. And from the spreadsheet that I generated, I made several graphs. The first one was a histogram comparing the observed to the expected regional discrepancy. What I found very interestingly was that the expected discrepancy exceeded the observed in terms of the mean and the median values. And I'll explain why this is significant in just a bit. Then I made some scatter plots. The first one plotting the observed to the expected discrepancy just to better see the relationship between the two. And I found that there was a low correlation, a low relationship, weak relationship between the two. Then I found scatter plots for the other 3 statistics, the resolution, occupancy, and the symmetry, and plotted them against the observed discrepancy to see their effects on the regional structural quality. And what I found, very interestingly, was that none of those statistics had a significant effect on the regional structural quality. And in fact, the resolution had the greatest effect with a correlation value of 0.166. I moved that so you guys can see that. And the other 3 statistics, the symmetry had a correlation of 0.002, and then the atom occupancy 0.014. So since the resolution was found to have had the greatest effect on the regional structural quality, I then made another scatter plot comparing the resolution to the expected discrepancy to see how accurate existing methods were for predicting the regional structural quality. And I found that there was an even weaker correlation with a correlation of 0.055. Now, the big question, what do these results all mean for the field of structural biology going forward? Well, the first thing is that since PDB-EDA has now been expanded to analyze not just small spherical regions, but also more complex regions around more complex ligands, this is very significant because now PDB-EDA is now much more versatile and can be used for many more studies. So for instance, a researcher that found a new protein, a more complex protein with a more complex ligand, they would need to first make sure that that protein is modeled as clearly and as accurately as possible. And to do that, they would need to use this software tool, PDB-EDA. And then they could then make conclusions about what that structure's functions are. And so that's the first major implication from this study, a very important one at that. And the second implication is that none of the statistics had an effect, a very high effect on the regional structural quality. And this means that there's a greater need now to find other statistics to replace these 3 statistics, the resolution, occupancy, and the symmetry. And so and another reason why this is needed is that the expected discrepancy, which refers to current methods of predicting the regional structural quality, were found to be inaccurate, as evidenced by the low correlations between the expected and the observed discrepancies and the expected and the resolution values, and the histogram showing that showing the expected to the observed discrepancies. And so now there's a need to find other statistics so that the current method of just using the regional discrepancy is not used anymore, because now that method is not very accurate. So to name other statistics that could be used to replace the symmetry, occupancy, and the resolution, one of them is the evaluation of bond lengths. Since bond length, within each bond, there are electrons that can affect the overall electron density and thus the amount of steric hindrance within that region, thus affecting the regional structural quality. And another metric that could be used is the type of ATP, the type of binding domain. So for instance, for an ATP ligand, the 2 most common binding domains are Walker A and a Walker B motif. And so if there are found to be a difference between these 2 binding domains, that would be very significant, and that would be used to evaluate the regional structural quality. And that would make sense since the binding domain dictates the type of structure that it is, and thus what kinds of functions it has. So now I'd like to thank the Kentucky Young Researchers Program for allowing this project to happen, to take place. Then I'd like to thank the Math, Science, and Technology Center and Ms. Karen Young for providing me guidance and support for this project. And lastly, but not leastly, I thank Dr. Hunter Mosley for helping me to conceptualize this study and for giving me advice and support along the way. And I also thank Dr. Sen Yao for creating the previous iteration of PDB-EDA that I then expanded upon for this study, as well as for offering me advice on how to use the relevant structural visualization software. And with that, that concludes my presentation on my research. Thank you very much for listening.